In this video, we're going to be talking about titrations as they apply to acid-base reactions and how we can use titrations to solve for the concentration of an acid or base solution. So a titration is just an experimental method of determining an unknown concentration. And so if you want to determine the concentration of an acid or base, a titration is a really common way to do that. Since acids and bases react with one another in such a simple and predictable way of proton transfer, titrations are a great way to determine the concentration of an acid by reacting it with a base, or base by reacting it with an acid. So in order to use a titration in this way, we need to know both the volume and concentration of one reactant as well as the volume of the unknown solution. So for one of our reactants, we need to know both the volume and the concentration. For the other one, if we know the volume, we can find the concentration. So in this first example here, if 50 milliliters of 0.01 molar barium hydroxide are required to neutralize 75 milliliters of hydrochloric acid, what is the molarity of the hydrochloric acid solution? So the two things that we're reacting here are barium hydroxide and HCl, and we can see that we have the volume and the concentration of the barium hydroxide. So we know both of these things about our barium hydroxide solution, but we only know the volume of HCl, and we're asked what is the molarity of that HCl solution. So we can do this by first writing our reaction. So we need to identify what is the reaction that is happening between these two substances, because the stoichiometry, the coefficients of that reaction, are the key step in this process that allows us to use a titration in this way. So we have HCl reacting with barium hydroxide, and we only need the molecular equation for this. We don't need the net ionic. It is the stoichiometry of the molecular equation that matters here, so that is the one we want to work with. So double replacement type reaction here. The cation of our base is barium, is going to swap places with the H. And so we're going to end up with barium chloride and water. Note that because barium has a +2 charge and chloride is -1, we need 2 chlorides for every barium. So just like every other reaction we've written involving ionic compounds, the charge on each compound has to add up to 0. Similarly, with the water here, we have hydroxide gaining a single H+ to become water. So this reaction is not currently balanced. We are going to need 2 HCl to get these 2 chlorides that we need, and that is going to end up producing 2 waters. So the way I like to think about neutralization reactions in terms of balancing them is that every hydroxide ion needs an acidic hydrogen. So when I look at this, I see that I have hydroxide, and I have 2 of them. So each hydroxide ion is going to gain 1 H+. My HCl only contains a single acidic hydrogen. So in order to completely neutralize both of my hydroxides, I'm going to need 2 moles of HCl. So personally, that's how I think about neutralization reactions, is that each base needs an acid. Essentially, HCl only has 1 acidic hydrogen, but barium hydroxide contains 2 hydroxides. So I need 2 moles of my acid for every 1 mole of my base in order to completely neutralize them. So essentially, there are kind of 3 steps to the titration math. We need to first find moles of one of your reactants, whichever one you know the most about. So in this example, that's going to be the barium hydroxide. Since we know, parentheses, since we know both the volume and the concentration of the barium hydroxide, we'll be able to figure out the moles of that substance. Remembering that molarity is moles per liter. To find the number of moles, we just need to multiply by the volume in liters. So 0.01 times 0.05 is going to be 5 times 10 to the negative 4th moles of barium hydroxide that reacted in this situation. So these numbers, again, are coming from what we were given in the problem, the molarity and the volume. So the next thing we need to do here is find moles of the other reactant. And we're going to do that using the coefficients from our balanced reaction to just convert from one to the other. So we know now that we have 5 times 10 to the minus 4th moles of barium hydroxide. So we need to convert from moles of barium hydroxide. So that one's going to go on the bottom so that that unit will cancel, into moles of our other reactant, which is HCl. So that one is going to go on the top. So this number, again, is just coming from what we just calculated. This is going to be based off of our coefficients. So we had a coefficient of 2 in front of HCl and an invisible 1 in front of barium hydroxide. So for every 1 mole of barium hydroxide that reacts, there must have been 2 moles of HCl present in order to completely neutralize it. So that means that our 5 times 10 to the minus 4th moles of barium hydroxide must have reacted with 1 times 10 to the minus 3rd moles of HCl. Running out of colors. Sure, darker green. So we now have the number of moles of HCl that were present in our system. Just move the next example out of our way. And the last thing we need to do is find the molarity that we are interested in here. So remembering that molarity is just moles divided by liters. We're looking for the molarity of HCl in this problem. We just found the number of moles of HCl, and we already knew the volume of HCl from back at the beginning of the problem. So our molarity is just going to be moles divided by our volume in liters. So it was 75 milliliters, which is 0.075 liters of that solution. So we have this value that we just calculated, this value from earlier in the given information is going to be 1.3 times 10 to the minus third molar is our molarity. So we're really just using our understanding of what molarity means as the number of moles in a liter of solution, coupled with a little bit of stoichiometry, allows us to use titration data to figure out the concentration of an unknown solution. So with that, I would like you to take a few minutes to try this next one on your own, and then we will go through it together. Remember that you need to write a balanced neutralization reaction first. And each hydroxide needs an H+ to go with it. So in this example, we have 3 acidic hydrogens. So each of those acidic hydrogens is going to need an OH- in order to neutralize it. So think about how that's going to affect your balancing. So first thing we want to do is assess kind of what do we know and what are we trying to figure out. So we're told that we have 60 milliliters of a 0.5 molar sodium hydroxide solution that is neutralizing 150 milliliters of phosphoric acid solution, and we're looking to find the molarity of that H3PO4 solution. So first things first, write our reaction. We need to know what's going on in order to be able to solve this. So we have H3PO4 reacting with NaOH. When I look at this, I see that I have 3 acidic hydrogens in this molecule, which means I'm going to need 3 hydroxides in order to completely neutralize those. But sodium hydroxide only contains 1, so I'm going to need 3 moles of base for every 1 mole of acid in this neutralization reaction, and that should work out in the end. So when our ions, when we write our products, our sodium and our hydroxide are kind of going to change places here. Since sodium has a +1 charge and phosphate is -3, we need 3 sodium ions for every phosphate. And each hydroxide only picks up 1 H+, so we will end up with 3 water molecules produced as well. So calculations-wise, the first thing we want to do is work with whatever we're given the most information about, which is our sodium hydroxide, to find the moles of that substance. So we know that this was a 0.5 moles per liter solution of sodium hydroxide, and we had 60 milliliters of it, or 0.06 liters. So that means that we reacted 0.03 moles of sodium hydroxide. So the next thing we need to do is convert that to moles of our acid, to moles of the phosphoric acid. We had 0.03 moles of sodium hydroxide. We want moles of sodium hydroxide to cancel, so that goes on the bottom. we're interested in finding moles of H3PO4, so that goes on the top. So we just need to pull our coefficients from our balanced reaction. H3PO4 has a coefficient of 1. Sodium hydroxide has a coefficient of 3. So for every 3 moles of NaOH that reacted, there was only 1 mole of H3O4 present. H3PO4, I think I said that wrong the first time, which means that we had 0.01 moles of phosphoric acid present in our initial H3PO4 solution that we're trying to find the molarity of. And then the last step is taking that number of moles and dividing by the volume, which was 150 milliliters, or 0.15 liters of that solution. So this is going to come out to 0.067 molar H3PO4. So all we did here was take the information that we were given about the sodium hydroxide solution, and we used that to find how many moles of sodium hydroxide were present in that sample. Then we converted moles of sodium hydroxide using our stoichiometric coefficients, invisible 1, to find how many moles of H3PO4 must have been present in that solution, and then divide by the volume we were given to find our final molarity.